case is state space representation using physical variables. Now, so in physical variables, let us take electrical system as example. We can derive the state model for any physical systems like mechanical system, hydraulic system, pneumatic system. Any physical system we can derive very easily. Let us look at the electrical system first. So in physical variable form, whenever you have the electrical system, we have to look at what are the energy storage elements we have. The energy storage elements are inductors and capacitors. So when you take the state variable, generally we take the inductor current is one state variable and capacitor voltage is another state variable. So depending upon the capacitors and inductors, then you will get the order of the system, and depending upon the order, then we will have state variables of the system. Now, as I said, the inductor current and capacitor voltage, these two are the state variables we assume in the electrical system. Let us look at with one example and how can we get a state model using the physical variables. Let us take this electrical system where I have R, L, C which are connected in series. It is series RLC system, very famous second order system. Now, so resistance is R and inductance is C and capacitance inductance is L and capacitance is C. And this system I am giving excitation input voltage Vi and I am getting the output voltage V0, or we can assume this is V1 and V2. So two voltage input and output. The transfer function what we want, the state model what we want is the output voltage to input voltage. So this is what we want. So output voltage is the output node and input voltage is the input node. And so with that then we can build the state model where we have x1, x2, x3 are the state variables. Now let us take one example and see how can we model using the physical variables. Now, so let us take this circuit. This circuit is having a resistance, inductance and capacitance, and all are connected in series, and Vi is the input, let us say V1 is input and V2 is the output. Now, so for this system let us prepare a model using the governing equations. Now, so I am assuming loop current here I, and there are two storage elements, one is inductor and capacitor, and as we know that the inductor current is one state variable and capacitor voltage is another state variable. The inductor current which I am taking it as IL and capacitor voltage which I am taking it as VC. IL, VC are the two state variables. When you derive the state model, then IL dot VC dot is equal to some A matrix into IL VC and also input Vi, and output V2 is something into your state variables and as well as your D matrix into your input variables. Now, so we will write KVL equation in the loop 1. When you write KVL equation in the loop 1, it is very clear. R into I plus L di by dt plus 1 by C integral I dt is equal to Vi. So this is the KVL equation. Now we know that the capacitor voltage we can write it as Vc is equal to 1 by C integral I dt. Therefore wherever this term is there, I can replace it with Vc. So I can write now Vi is equal to Ri plus L di by dt plus Vc. Now in this equation I have L di by dt where this small I is similar to the capital I. So I can write it as small I is IL, which is one of the state variable. Then I can write it as dIL by dt is equal to, this is nothing but the IL dot, and the inductor L you can take into other side and you can write the equation as, so V1 by L minus R by L, we have IL minus we have 1 by L into Vc. So Vc is a state variable, IL is a state variable where V1 is the input variable and where IL that is the state variable. So whenever you write equation, the left side you should have the state variable derivatives, right side some constant or coefficients with your state variables and input variables. No other intermediate variable is allowed in the equation when you write the final equation 2 before deriving the state model. Then I can write the capacitor voltage. The capacitor voltage is CdV, capacitor current is CdV by dt. Capacitor voltage is Vc, which is one of the state variable. With that I can write the current through the capacitor. The current through capacitor small I is equal to CdV by dt or dVc by dt. Where small I is nothing but capital IL, that is which is my inductor current one state variable. So I can write it as a dVc by dt is equal to, that is Vc dot is you have 1 by C into IL. This is the second equation. What is output? Output voltage is V2 is nothing but Vc. So with these three equations I can build the state model as IL dot Vc dot is equal to, what are the entries of A? So we have minus R by L, and we have minus 1 by L, and we have 1 by C and 0. This is A matrix, and along with that state vector which is IL Vc, plus in the input matrix is 1 by L and 0, and the input is V1. But output V2 is nothing but 0 1, which is the C matrix, and IL Vc is my state vector, plus we have a 0 here D matrix into V1. So this way we can get the state model for the given electrical system. Similarly, we will see one more circuit and see how can we develop the state model using physical variables. Look at this circuit. So in this circuit there are many elements. When you look at here, this is a voltage source, and we have R1, L1, and there is shunt element C, and I have R2 and L2 and R2. So once the electrical network is available, the first thing is how many storage elements are there in the system. Therefore we can find out the how many state variables that are need to be write the equation. So there are three elements L1, L2, C, which are the storage elements. Then inductor current IL1, inductor current IL2, and capacitor voltage Vc are the state variables. So with those state variables, then I can finally write the state model. Therefore take the loop 1. There are two loops. We can write the KVL equation loop 1. So when you write the KVL equation loop 1, minus V1 plus R1 I1, because I am taking the I1 is a loop current, but L1 di1 by dt plus 1 by C integral I1 minus I2 dt equal to 0. Now the small I1 loop current is nothing but the capital IL1, which is nothing but my inductor current, one of the state variable, and a small I2 is IL2 is another state variable, and 1 by C integral I1 minus I2 is Vc, another state variables. So I am going to rewrite this equation in terms of the state variables, and the left side I want to write the L di by dt, where which is nothing but my first loop I1 term. So when you rearrange this, you will be getting it as a dIL1 by dt, which is IL1 dot state variable derivative is equal to V1 by L1 minus we have R1 by L1 into IL1 plus minus Vc by L1. So this is the equation, one of the equation. Before deriving state model, when you write the equation, we got the one of the equation. Similarly, we can write the loop equation in KVL equation in loop 2. When you write KVL equation loop 2, there are no sources at all, then we can write directly R2 I2 plus L2 di2 by dt plus 1 by C integral I2 minus I1 dt is equal to 0. Then again I have small I1, small I2 replaced with the state variables IL1, I2, and also Vc, the state variable is 1 by C integral I1 minus I2. So when you use these things and we write the equation, second loop equation, then we will be getting, when you rearrange the terms, and we will be getting the second state variable equation as dIL2 by dt, that is IL2 dot is equal to Vc by L2 and minus R2 by L2 into IL2. So this is your second equation, which is useful for us. Next is we have capacitor. So capacitor, I am going to write the current through the capacitor. So what is the current through the capacitor? I1 minus I2 is equal to C dVc by dt. What is this I1, I2? These are the loop currents, and we know that this I1, I2 also my inductor currents, capital IL1, IL2 state variables. Now dVc by dt available. So what I can write here? dVc by dt is equal to, which is nothing but Vc dot is IL1 by C minus IL2 by C, which is the third state equation. So using these equations I can develop the state model. So when you writing the equations, whenever you have inductor, we are always to write the voltage equation. Therefore I will get L di by dt, di by dt I can write left hand side, I can take everything into right hand side. But whenever you have capacitor, always write the current equation. So once the current equation is written, then you will get C dVc by dt. Therefore dVc we can by dt we can write left hand side, keep it, and other things you can keep other side so that I will get the state equations. Now, so when you look at the state model, in this case the state model I1, IL1, IL2, Vc, these are the state variables. Then dot gives the derivative of the state variable is a matrix, and also we have the state variables IL1, IL2, Vc plus input matrix, and V1 is the input. Now when you write entries into these matrices from the equation 1, it is very clear. Then the first row elements are minus R1 by L1, and we have 0 minus 1 by L1, and again in the input matrix we have 1 by L1. Similarly, when you look at the second equation, we will be writing it as a 0 first element, then we have minus R2 by L2, and also we have 1 by L2, and input it is going to be 0. Similarly, we have the third equation where we see dot. So if you third equation, if you look at that, then we can write entries as 1 by C, and also we have minus 1 by C, and also we have 0, and there also 0. So this is A matrix and this is B matrix, which is a state equation. So if you want to write the output equation also, we can write output, we are taking at the voltage across the resistor, which is V2 is equal to R2 into I2 small I2, but small I2 is the capital IL2. So when you write the equation, your V2 becomes 0 R2 0 into IL1 IL2 Vc plus 0 into V1. So this is A, B, C, D matrices, and with these matrices we can write the state model.